part 2 today, we're going to look at an example of where this concept of filtering is particularly useful. Okay? So one common circuit that we see nowadays in the real world is something called an inverter. Okay? What an inverter will do is it will take a DC input and turn it into an AC input. Now, that's a complicated circuit that involves a lot of switches and transistors, so it's a little bit beyond the types of things that we would probably want to look at in this class. Okay? It's what we call a power electronics circuit. But fundamentally, it's used very commonly if I have solar power that I want to connect into the grid. So if I have a photovoltaic panel or a solar panel, right, that solar panel produces a DC voltage. So the DC voltage that I would get is this yellow waveform. So this is a real waveform, right? So this yellow waveform is the DC voltage coming out of this PV array, this solar panel. And the green here is basically the 60 hertz grid, 60 hertz voltage, right? So connected over here. So on this side I have the grid, all right, what I would call the grid, which is essentially an AC voltage that is this green guy. Okay, so I had DC in and I've got AC out. So what this circuit does is it basically is a chopper, right? It converts that DC into this wild looking AC waveform here. If I really zoomed into that AC, what I would see is that yellow waveform is basically varying really, really fast between 0 and whatever the panel voltage is. Okay? Well, if I take that particular voltage and I pass it through a filter, I can effectively create a cosine waveform or a sine waveform like what I have in the green. Okay? That's the basic idea of what this circuit does. And filtering is really important in this particular case. Okay? So if I look at the way I would operate this type of a circuit, all right, here's another view of it. So I take a solar panel, hook it up to this thing I call the inverter. And the filter typically looks like this. I have an inductor, a capacitor, and another inductor. So this guy here I would call L1, this guy L2, and this guy C. And this is my grid voltage, which is that, sort of sine wave sort of thing. Well, ideally, what I do is I control this circuit in some way that I measure the current. So what I do is I'm saying I measure the current right here in this inductor. Somehow pass a measurement of that into a microcontroller, which tells this circuit what to do. Okay? So in this particular case, our goal is for I sub G, the actual current right here. I want that current to basically be just, in this case, 2 amps times cosine 2 pi 60t. So one thing we haven't said yet is the frequency of this voltage is 60 hertz, okay? Or 2 pi 60 radians per second. So I want the current that I put into the grid, in fact, not just one, but I am required essentially by law and regulation to basically make sure that the current I put into this grid has exactly the same frequency and phase as this voltage does. Okay, in this particular case, I want the amplitude to be 2 amps. Well, because of the way this circuit functions, however, this actual current coming out of the inverter, I sub L, has this form right here. So 2 cosine 2 pi 60t plus I noise. So what that would look like is something like what I've shown here at the bottom, right? So I see the 60 hertz. That's this sort of low variation right here. And then on top of it is this noise, which is basically up and down. So I've zoomed in on that noise. So basically right around here, all right? All right, if I take that and I explode it and look at what's going on, I see something like what I've got up at the top here, okay? Now, in this case, this guy here, my underlying variation is 60 hertz. The guy at the top here, if I look at the period, so this is 0, 10 microseconds, 20 microseconds. So 1 times 10 to the minus 5th, 2 times 10 to the minus 5th. This guy has a period t of 1 over, well, I guess I should say 10 to the minus 5th. So the frequency here is 10 to the 5th hertz. That's 100 kilohertz. Okay? So in this particular case, my noise has a frequency of 100 hertz. And then the signal that I want, all right, has a frequency of 60 hertz. So I can think of IL of t as this 2 cosine 2 pi 60t plus IN. Now my goal would be to get rid of that IN. Okay? So in this case, I'm saying I want to keep a low frequency and I want to get rid of a high frequency. So that means that ideally I should be looking for what I would consider to be a low pass filter. So I want to pass the low frequencies and attenuate or kill off the high frequencies. Okay? Well, in this case, I'm going to try to articulate that in a certain way. So when a designer does this, just to be clear, the transfer function I'm after right here is I know what IL is. So IG over IL is my H of S in this case. Right? I know what IL is, and I'm interested in IG. Okay? So if that's the case, let's just think of this guy as a box. I have IL as my input. I have IG as my output. Okay? So IG over IL is my transfer function. I know that if I have S equal to 2 pi 60j, I want the magnitude of this guy to be 1. In other words, I want the input and the output to have the exact same amplitude. Okay? In other words, my 2 amp input at 60 hertz should be a 2 amp output at 60 hertz. But I also have a term that's sitting out here at 100 kilohertz, right? At omega equal to 2 pi times 10 to the 5th. Well, in this case, what I'm going to say is I want the magnitude at that frequency to be less than 1%. Okay? In other words, I want it to be the magnitude at that frequency to be less than 0.01. What that means is that at this particular frequency, my output, so my output I sub g at omega equal to 2 pi times 10 to the 5th will have an amplitude less than 1% of the input amplitude. Okay? So if you looked at this guy here, you see that the waveform I have coming in has a 1 amp amplitude. Well, what I'm saying is I want that 1 amp amplitude to become 1 times 0.01, right, or less than 1%. So 1 times 0.01 is 0.01. So I have 1 amp in, and I'm 1 amp in, and I'm getting 10 milliamps out. So as I'm reducing that 1 amp signal to a 10 milliamp signal or less, all right, possibly less than 10 milliamps. Okay, so what I do is I take a look at this circuit. If I have L1, L2, and C, okay, so I know what IL is. So I know IL, I need to find IG. So since I know what IL is, what I'm really after here is I'm really after trying to figure out what is IG. Now, because I have V grid, I got to use superposition. So in superposition, if I have a voltage source, I set that voltage source equal to 0, and I have a capacitor in parallel with an inductor L2. All right, so if I have that scenario here, okay, what I do is I say, let's figure out the transfer function. So in this case, if I know IL, I have a current divider. So the way that I look at a current divider is I basically say, all right, so if I know IL, I first figure out the voltage across this parallel combination, so V. The voltage across that parallel combination would be IL times the impedance. The impedance would be 1 over SC in parallel with SL2. Okay? That voltage divided by the impedance of this branch right here will give me IG. Right? So IL times this impedance divided by SL2 tells me what IG is. If I expand that whole guy out, then what I get is that IG equals IL times S squared L2C plus 1. All right? Which tells me that my transfer function H of S is 1 over S squared L2C plus 1. Now, let's remind ourselves, or in this case, I guess how I designed this is I chose L2 equal to 100 microhenries and C equal to 10 microfarads. Okay? So if I do that and I plug in those particular values, what I'll find is that H of J 2 pi 60, all right, the magnitude, if I plug that into this transfer function, which just bear in mind would be the magnitude of J 2 pi 60 squared L2C plus 1, whatever the magnitude of that is, right? You could do that conversion. In this case, I find that this is equal to 1.0001, so that's really close to what I wanted it to be. And if I do the magnitude at 10 to the 5th, this guy becomes equal to 0.0025, which is definitely less than 0.01, which is what I wanted it to be. Okay? So what that means is that my 2 amp signal at 60 hertz will still be a 2 amp signal at the output. But my 1 amp signal here will become a 2.5 milliamp signal. So in other words, I made that noise signal much, much smaller, and I sub G, if I look at it, is going to look like that, right? So I have crazy waveform coming in to my filter, and my output is basically just the low frequency part of it, okay? So that's a low pass filter, and this is a pretty common application where I have some sort of quote-unquote noise signal that I want to get rid of, and the goal of the filter is to keep the stuff I want and to get rid of the stuff I don't want. All right, now this raises kind of an interesting problem in general. So if I take my magnitude, h of j omega, okay, which just to be clear, remember h of j omega is 1 over j omega squared L2C plus 1, right? If I take the magnitude of that and I plotted it versus frequency, I get something that looks like this. And that looks pretty strange to me, because what I see is that at some particular point, right, some particular point, this guy becomes over 70,000. In other words, there's some frequency at which the input is actually much, much bigger. Well, sorry, the output is actually much, much bigger than the input. But then everywhere else, the magnitude of this guy is really, really small, okay? Now, I would get that by just computing the magnitude of h of j omega from this guy right here, all right? This kind of creates a problem because I can't really see most of this function because the scale of that y-axis, the scale of the magnitude is just so thrown off. So we have a special tool to be able to deal with this. That special tool is a logarithm, all right? So if I take, you should remember this, if I take the log of a number, let's say I'm going to say the log base 10 of the number 10, I get 1. If I take the log base 10 of the number 100, I get 2. All right? Logarithms are a different way of expressing values, and we often use logarithmic scales to express values when I have a really crazy set of values that I want to look at all at once. So looking at our transfer function, we said the magnitude in this case goes up to like 70,000 and then goes down to values below 0. Okay? So what we do is instead of plotting the magnitude, we plot the logarithm of the magnitude. So in this case, and for historical reasons, we typically do 20 times the logarithm of the magnitude. All right. Now I specifically say log base 10 because one thing I want to point out is your calculators are usually you say ln if you mean log base e. In MATLAB, log is the same as ln. You probably didn't learn it this way, right? So in MATLAB, if I want the log base 10 of something, I say log 10. All right, is the command in MATLAB. So the command log is the natural logarithm, and log 10 is what you're probably used to considering log. Okay. All right. So anyway, just a quick aside on that. All right. So what I do is I take this crazy looking magnitude, I take the logarithm of it and multiply it by 20. Again, that multiple of 20, just accept it. It's an artifact of history. All right. We call this 20 times the log of the magnitude of something. We call that a decibel. All right. In many cases, you probably heard that term before, we talk about sound levels often in terms of decibels. So something that's very large has a high decibel value. Okay. Now what we did here is not only do we plot this magnitude as a function of a logarithm, but I plot the frequency axis also on a logarithmic scale. So if you look at this, I'm plotting essentially between 1,000 radians per second and 1,000,000 radians per second. But what you see is that on this scale, there's an equal spacing between 10 to the third and 10 to the fourth, and an equal spacing between 10 to the fourth and 10 to the fifth, and an equal spacing between 10 to the fifth and 10 to the sixth. Obviously, there's a lot more space between 10 to the fifth and 10 to the sixth. But if I take the log base 10 of those numbers, so the log base 10 of, let's just try this real quick. The log base 10 of 10 to the third is 3. The log base 10 of 10 to the fourth is 4. The log base 10 of 10 to the fifth is 5. The log base 10 of 10 to the sixth is 6. Okay, if you don't remember that, go back and practice logarithms because you're going to need to know those. Okay, and there's some problems on homework 9 that are going to basically review logarithms and exponentials for you. But if I look at this, what I see is that on the logarithmic scale, the log of 1,000 is 3. The log of 10,000 is 4. The log of 100,000 is 5. The log of 1,000,000 is 6. So on the logarithmic scale, the space as I go through what we call a decade, all right? So this space right here is called a decade. And this space right here is also called a decade. And this is called a decade, right? That space between frequencies that are separated by a factor of 10 are equally far apart from each other on a logarithmic scale, okay? Now notice the critical thing about what happened here is it's really hard to see on the absolute magnitude what the heck you're looking at except at this one point. But if I take the logarithm of h of j omega and plot it on a logarithmic axis, now suddenly I get a much more meaningful graph. Now how would I use that here? Okay, well, so what I would do is I would look to say, well, what is the magnitude at the frequencies that I care about? Okay, so as an example here, so what I have is, so in this case, right, we said our two signals that we had, one of them was at 2 pi 60 and one of them was at 2 pi 10 to the fifth. Okay, now we said that at 2 pi 60 the magnitude was 1.001, and we said that at 10 to the fifth, right, and I should be careful, right, I actually 2 pi 10 to the fifth, right, the magnitude was 0.0025. Okay, so in this case, what I did was I put those numbers in. All right, if you do 2 pi 60, it's about 375. It's actually closer to 377, but it was really hard to get that on my graph. Okay, what I see is the magnitude in dB is 0.00123. Okay, so what that means is 20 log of the true magnitude at that frequency is 0.00123. So to get that back, in this case, basically what I have is 20 log 10 of h of j 2 pi 60, okay, is equal to 0.00123. So that means that the log is h of j 2 pi 60. That's equal to 0.00123 divided by 20. So to figure out what this guy is, this is our unknown value here, I raise both sides to the power 10, like that. Right? That's how I undo the logarithm. If you don't remember that, you're going to have to go back to your high school math to remember that. H of j 2 pi 60 magnitude then is equal to 10 to the 0.00123 divided by 20. You calculate that, you get 1.0001, which is exactly what we did when we just plugged it straight into the equations. Now, if we put in omega equal to 2 pi times 10 to the fifth, which if you calculate it's about 629 times 10 to the third radians per second. If I look at the graph, so at that point, when the frequency is equal to 629 times 10 to the fifth, so that's right here, okay, the magnitude at that point is negative 51.9 dB. So notice these things kind of nicely fall into the same scale, and I can see them now. So I plug in that negative 51.9 and go through the same approach like I did up here, and I find that the magnitude at 2 pi 60 becomes 0.0025. Put that in your calculator into MATLAB and you'll see that you get that result, right? That's the same thing we had when we did the math over on this slide. So the critical thing in doing this is I took this thing that went from basically 70,000 to 0 and I made it such that I could really see all of what was happening. And the use of logarithmic scales is used all the time. All right, it's particularly used a lot in circuits. It's used a lot in economics and finance when people are trying to look at numbers that are changing rapidly. Okay, and trying to understand, you know, sort of at a finer scale what's really happening. Very almost impossible to see what's happening in a graph like this, whereas this guy allows us to really see it. All right, so we're going to explore this a lot more. This particular frequency response, this way of drawing it versus logarithms, is known as a Bode plot. And it's named for the person, Heinrich Bode, that created it at Bell Labs back in the 1930s. All right, we use that terminology, and it's very common for us to make use of it. But it's very important to take away from today's problem that this is a very real issue, right? Where I have a very practical system, right? That I take a DC and want to go into the grid, and I get this crazy signal that looks like this current right here, but I can't have this signal. So this signal is the additive version of the one I want, which was 2 times cosine 2 pi 60t. That's the signal I wanted, but I also had this noise. So this filtering concept allows us to do things like keep the things we want and get rid of the things we don't want. And we use that all the time in all kinds of applications like power, radio, audio, right? You can kind of think of that. If you have bass control in your stereo system, for instance, bass control is basically amplifying the bass signals. Those are the low frequency signals, and not doing anything to the high frequency. That's some kind of a filter. Same thing with treble, except treble is operating on high frequencies instead of low frequencies. So we'll be talking more in the coming days about how we generate these types of graphs. All right. So we're going to assume very often that we have a circuit and we have a transfer function from that circuit, and we want to figure out how to generate this graph and understand what this graph looks like.